we do not have a 2 to the power of something. It's not a power of 2, of those in a day. So we have to redefine, what a second is, or what is the smallest unit of time that we use on the day. Yep. All right, so it is noontime, so we're gonna get started. The first thing we'll do, or the first thing I'm gonna do, is to go over the homework assignment, okay, which is kind of in the form of a quiz, but you have an entire week to work on it, okay? So that's the first thing we'll do. If you have any questions about those concepts, you probably want to bring it up as we go over the homework. There won't be any homework today, but I might give you some ungraded assignment just like before, so that you have something to think about. All right, so this is set theory, and I'm just going to do a preview so we can go through all the questions. All right, so this is question number 1. Set A has 2 elements, lowercase a and lowercase b, and uppercase B as a set has 3 elements, lowercase a, b, and c. Which of the following is true? Okay, the first one is A is a subset of B. Yeah, that sounds about right. Okay, because every element of A can also be found in B. Okay, but we don't want to pick anything yet. Okay, even though it looks right, we want to kind of go through all of them to make sure the other ones are false, just to be sure. The second one is A is an element of B. No, that is not the case, because we would need a set with elements A, B in B in order for set A to be also an element of B. So the way it is right now, A is not an element of B. Uppercase A is not an element of uppercase B. B is a subset of A. That is not true, because an element C is in B but not in A. Okay, so B is not a subset of A. B is an element of A. That is also false, because neither set has as an element a set. Okay, so neither set can be an element of the other one just because of that. Do we have any questions about number 1? Okay, moving on to number 2. So I'm going to pick the correct answer here. Okay, number 2 has to be manually graded. So if you're not getting those 3 points, that's absolutely normal, because I have to go in to take a look. So let's take a look at what the question is asking. Given that A union B has A, B, C, D, E all lowercase in it. Okay, so these are the elements in the union of the 2 sets A and B. The difference between A and B, or the elements that are in A but not in B, are C and E. Define a membership arrangement of A and B. In other words, tell me an example of what can be in A and what can be in B to satisfy the constraints. The constraints being the union between A and B has these 5 elements, and then the difference between A and B has C and E as those elements. So you want to type your answer in the HTML editor area and use all the correct notations, which basically means you have to remember to use curly braces to enclose elements in a set. Okay, for the most part, that's basically what I mean by that. Okay, so for those of you who like to use fancy tools, you can use the math editing tool, which looks like this. Okay, but you don't have to do this, because the symbols that we are using are simple enough that we do not need to use that tool. Okay, so it doesn't really matter which way. All right, so let's start with A and try to figure out what has to be in A. Well, what has to be in A is already suggested here, because A minus B tells us everything that is in A but not in B, right? So I have no choice. C and E must be in A. All right, so we have C and E that must be in A. Then we look at this and go like, well, can A just have C and E as its elements, and then we'll just work with B to satisfy the constraints? The answer is, yeah, we can do that. Because the other constraint is A union B need to have A, B, C, D, E. Well, since we already know that A has elements C and E, we locked that down earlier, we can now just say that, well, everything else in the union would have to come from B. Yep.
Would it still be correct if A, B, and D were also included in
Yes. So we'll see what happens here. Okay. So don't copy this because this is actually not correct. Okay. So we will say B will contribute all the other ones. So the other ones would be A, B, D, right? So those three elements. But this answer is actually incorrect. Let's see. Would it be incorrect? No, this is actually correct. It would satisfy both constraints. This is actually correct. Because if you ask, if I look at all the elements in A and all the elements in B and put them all together, do we get A, B, C, D, E? Yep, we got A, B, C, D, E. We're good, okay? We satisfy the first constraint. The second constraint says, if I look at all the elements of A and all the elements of B, do we only have elements C and E that are in A, but not in B? Let's see. A does have C and it does have E. Are those missing in B? They are missing in B. So this satisfies both requirements, both constraints. But this is not the only answer that works. There are many other answers that will also work. Okay? So the second one that would also work is A actually contains everything. A, B, C, D, E. Okay? So if I tell you that A has A, B, C, D, E, how do you construct B to satisfy the requirements that we have just listed here? So A has CE, but B does not have CE, right? So in this case, B will need to have, it needs to have A, it needs to have B, it needs to have D, but it will have to miss C and E. Is that making any sense? So the second row is also a correct answer. And there are other correct answers as well. I'm just giving you the two extremes, making A as small as possible, making A as big as possible, and then there are in-between solutions that will also satisfy both constraints. So are we understanding this question? Are we understanding the concepts enough to answer this question? Yep. No, they're both equally correct. They're both equally correct because they both satisfy the constraints. Because I did not ask make A as small as possible or make it as big as possible. All right, so let's move on to question number 3. Choose the correct answer. Is either true or false, right? So the question is the value A, lowercase a, an element of the set that has an element which is also a set that has A in that set? So is the answer true or false? False. It is false. Very good. And then here we have this one, which is asking, is the set that has elements A, B, C a subset of the set that also has the elements of A, B, C? Yes. The answer is true. Every set is a subset of itself. So this is true. Question number 5. If I look at the union of A, B, C as a set and the set AB, do I get the set just A, B, C? Yeah. Yes, because we do not duplicate items in a set. So this is also true. Question number 6. Now these are starting to get a little bit kind of, some people asked me about these questions, because they didn't quite understand what I was asking, and that's perfectly fine because it is a little bit confusing. Regardless of the definitions of set A and set B, does the implication hold true? Okay, so to illustrate that that is not the case, you have to find me a counter example. Give me an example of what A is defined to be, give me an example of how B is defined, and that implication is false. Now, how do you make an implication false? The left-hand side has to be true, the right-hand side has to be false. So you have to find me a counter example that makes that happen. So you have to give me a counter. You have to give me a counter example where A minus B is in fact the empty set, but the negation of A is a proper subset of B is false. Now, if we say that A is a proper subset of B is false, that means A really is a proper subset of B. So find me an example such that A minus B is the empty set, but A is actually a proper subset of B. That would make it work. So what example can you come up with? Yep, go ahead.
If A is the set that only contains A,
Mm-hmm.
and B is the set that contains A and the set that contains A.
Okay, like that.
Yeah.
Okay, so we'll take a look at the first thing, which is A minus B. Everything that is in A only got one thing. And unfortunately, that thing is also found in B. So there's nothing that is in A but not in B. So we made the left-hand side of the implication true. Okay, so that's good. Okay, we're now moving on to the second step. Is A proper subset of B? It is, okay, because everything in A is also in B, but B has at least one extra item that is not in A. So A really is a proper subset of B. So if A is a proper subset of B, this part is true, the negation of that is false. So we have just made the right-hand side of the implication false. In other words, we now have true implies false. The implication itself is false. So the answer to this question is false. Yep.
So is the right-hand side of that just saying that A is not a proper subset of B?
The way it is listed here, yes. That's what it's saying. Yep. Some people put a cross or a bar or a line, across the subset, proper subset of, to say it is not a subset of. I just use a negation on the outside. Yep.
Could you just use the definition of implication to find out that that's already false, regardless of what's in there?
Not exactly, because the definition of implication does not say whether, in this particular case, the implication is always true or not.
I think what I mean is, if you look at the logic table,
Mm-hmm.
the ones and zeros,
Mhm.
the only false result is true, the left side is true, and the right side is false.
Right, right.
But it would implicate, it would
But
result
can it happen, right? Just because the operator can return false doesn't mean that you can find a case in this case to make it happen. Okay? Okay, so since we're on that line, in that line of reasoning, let me give you a particular implication that cannot be false. Okay? So the implication goes like this. Okay, so we have A is a proper subset of B. It implies A is a subset of B. Okay? I know you cannot see some parts of this. I'm just going to move here. So this implication is always true. You cannot make the implication false. Yes?
Are you streaming, by the way?
Huh?
Are you streaming, by the way?
I think so.
I didn't see OBS, so I'm asking.
Yep, it is streaming with audio. Okay, I just double checked. Okay, but this implication is always true. Remember, the only time you can make an implication false is the left-hand side is true, but the right-hand side is false. Right? Okay. So now we have to find a case where A is a proper subset of B, and that is true, and then A is a subset of B is false. Can you find me an example like that? The answer is no, you cannot find me an example like that. And now the question is why? Now, just because you spend an hour and cannot find a counterexample does not automatically make it true. So how do you prove that this implication is always true?
Like changing the proper subset to like the definition of proper subset.
Okay, so we use the definition. So this is one thing that is really important in this class is when you think about the problem, go to the definitions first. Okay, the definitions is the foundation. You start with the definitions. Then you try to see how you can make connections between the definitions and then start to use derivation to derive what you need. Okay? So what is the definition of is a proper subset of? How does A become a proper subset of B?
A is a subset of B.
A is a subset of B.
And there exists a value in B such that that value is not in A.
Okay. So can we say B minus A does not equal to the empty set? Okay, because something is in B but not in A, right? Okay, so we have that. And then we keep the other side, which is A is a subset of B. Okay, there we go. Now this is just straight out of the definition of is a proper subset of. Okay, there's nothing tricky about this. So from here, we look at this and go like, okay, where's my proof? Why can't I make the left-hand side true and then the right-hand side false? Okay, so the way you look at this is to simplify this a little bit more. Okay, so I'm going to use two Boolean variables x and y for this. Okay, we look at this and we just say, we'll call this x. So x is either true or false, right? And then we look at this part here and we say, well, this is somewhat independent of the first one. Okay, because A can be a subset of B and B minus A is an empty set. Okay, it is possible. Okay, because it's just a subset of but not a proper subset of. So we'll call that y. So if I use x as x, A is a subset of B, and then we use y as B minus A is not empty, then the entire left-hand side just becomes x and y, right? Yes? Okay. What about the right-hand side? Oh, that's just x, right? Now I say, I don't even care about subsets or differences between sets. Anytime you have anything that looks like this, you got x and y on the left-hand side of an implication, and you only got x on the right-hand side, this is automatically always true. It cannot be false. And you go like, why? Okay? I hope most of you are at least asking that question in your head of why, instead of, okay, text said this cannot be false, write it down. Okay? Why? Because, go ahead.
Well, because if x is false on one side, it must be on the other.
If x is false, it automatically makes the conjunction false, right? The only time a conjunction like this can be true is x has to be true. Now, y has to be true too, but x has to be true. Well, isn't that a contradiction if I want this side to be false and this side to be true? It cannot happen. Okay, so that's how we reason this out and basically say, okay, logically, this implication is always true. It doesn't matter what x is representing, doesn't matter what y is representing. The implication is always true. And somebody's going to say, well, but what if x and y are both false? They're just constant false, right? Well, that makes the conjunction false. If the conjunction is false, the left-hand side of the implication is false. If the left-hand side of the implication is false, the implication is true. Okay, so it goes back to the definitions again. So are we okay with this? All right, cool. And then we go to the next question. So the next question is kind of the same kind of format, regardless of how we define A and B. Is this implication always true? That's basically what it's asking. Okay. What do you think? A union with B equals to A intersect with B. I just spelled it opposite, but it's the same thing. Implies A is the same as B. It is always true, okay? This is always true. This one, the proof of this is a little bit, kind of beyond the scope, at this point anyway, but it kind of makes sense, right? Because A union with B is basically saying if something is in A or in B, it is in the union. Intersection is kind of the opposite. It has to be in both in order to be in the intersection. So if all elements we are talking about, in both of these, they're in both A and B, and they're in at least one of those two, that means A and B are really the same. Now, to prove something like this, proof by contradiction is the best technique to do it. Okay. Now, I haven't really introduced proof by contradiction at this point. So if you say I have no idea what is proof by contradiction, it's okay. Okay. There's nothing wrong. Okay. But if you once we get to proof by contradiction, if you remember this and go like, okay, Tech, can you go back to the first homework assignment and explain in question number 7 how we can prove this by contradiction? I will go ahead and do it to illustrate how we prove something by contradiction. But at this point, we'll just go like, okay, it can be proven by contradiction, but we're not going to go there, not at this point. Okay. The next one is question number 8. It says, A is an element of B implies that A cannot be a subset of B. Would that be true or false? It is false because we can construct a case where A is an element of B, but A is also a subset of B. That's pretty easy. We have done that many times. Okay. So are we good with the homework assignment? In other words, are we kind of pretty clear about these concepts? Subset of, proper subset of, difference. Yep.
So when you say membership arrangement, you literally just mean spell out the set.
Yeah, spell out what is the elements in the set. Mm-hmm. Yep.
So when it's false, it's because you can find one case that is false.
Because I can find one case where I can construct an A and a B, where A really is an element of B, but A is not a subset of B.
And then when it's true, the answer is true. It's when you.
Actually, I should say, A is an element of B, and at the same time, A is a subset of B, so that would turn the negation into false.
Yeah, and like for question 7, it's only true when you can't find a case that ends up being false.
Correct. It is always true in that case. All right. Any other questions? Okay, let me score my own answers because it would be super embarrassing on my part if I get other than the manually graded question, if I get anything wrong. Okay, that's great. Okay, this one needs to be graded manually, so it has not yet graded. 1 out of 1, 1 out of 1, 1 out of 1, 1 out of 1. All right, so hopefully you're all getting 7 out of 10 in this particular homework because that's the best you can do without me grading the question number 2. Are we good so far? Yep. Okay. So let's go back, and now we continue our discussion with in functions. All right. So we go back to functions. And we are almost done, if not entirely done, with functions at this point. But I'll just double check, make sure that it really is the case. Oh, right. Okay, so I had a huge digression the other day of, why do we need to use functions, okay? Or at least define functions the way that I defined here. Because in your math classes, functions are pretty structured, okay? Let's define f of x as 2x. F of 2 is 4, f of 3 is 6, f of 0.5 is 1, and so on, right? So you have an expression, how you map something from the domain to the codomain in most math classes. But in this class, the mapping from the domain to the codomain doesn't have to be structured, okay? It can reflect something that is completely, it's like, oh, things are going all over the place, okay? But why do we want to define functions where the mapping can be kind of all over the place? So the example that I was trying to show you was how do we specify that a sorting algorithm is getting the job done right, okay? So how would you do it? Okay, so let's just say that you are the professor, okay? You are giving your class a homework assignment and say, write a sorting algorithm. Okay? And then one of your students, who may not understand, a lot of, English words or specifically what sorting means in English, and ask, okay, can you define the proper output of this program? And not just say that, okay, the entries have to be sorted. So now you go like, okay, let me tell you, the properties of the output of this program relative to the input of this program. Okay, so you need to somehow use mathematical symbols to convey what do you mean by sorted. Okay, so the easiest way to specify something is sorted is like this. Okay, so you just say, so when the program exits, when the program terminates, I want this condition to be true. And somehow, miraculously, that student, not really understanding too much of English, understood all of these symbols. Like for all, the set notation, and element of, that sort of thing. Okay? Well, I mean, that can totally happen because, mathematics and the symbols that we use in mathematics are actually international. Okay? It is not localized to a particular language. So it is entirely possible that we have some students who say, I can totally understand this, but I don't understand the English description of what you mean by sorting. Okay, that's totally possible. So let's take a look at this and go like, okay, does it make sense? For all I in this particular set, what set are we talking about? This is a set that only has a few items. It is not an infinite, it's not a set with an infinite number of elements. We just want 0 to bar a bar minus 2. Okay, the notation bar a bar applied to an array really just returns the number of items in an array, size of an array. Okay, so we are just saying that if you choose any I from 0 to basically 2 less than the actual number of elements in the array, the following condition has to be right. Okay. So you say, okay, what happens when I equals to 0? When I equals to 0, then you basically say a bracket 0 is less than or equal to a bracket 1. Okay, that's kind of what sort of things to be in order, right? So when I equals to 1, then you're saying a bracket 1 is less than or equal to a bracket 2, and so on. Okay. So why do I choose bar a bar minus 2 as the bound, as the upper bound of those particular indexes? Because when I equals to bar a bar minus 2, then we'll be comparing a bracket bar a bar minus 2, which is the second last item in an array, and we'll be comparing it to a bracket bar a bar minus 1, which is the index of the last element of the array. So this way, we're basically just saying every element has to be less than or equal to the one right next to it. That kind of is what sorting should do, right? But it does not actually describe sorting at all. Because to make this happen, it's easy. I just have to reinitialize the entire array with one single value. Let's say 0. Would that be a sorting algorithm? No, but it does make this condition true. So that means that condition by itself does not describe the result of sorting. Are we doing okay so far with this description? Okay. So what do we need to do? Okay. So what we need to do is to introduce a function like this. Okay. So if you focus on where the blinky cursor is, okay, this is a function because I'm using f and then the colon and then the single bar arrow. So I'm saying that f is a function, this is our domain, and this is our codomain. You look at the codomain and the codomain, you go like, they're exactly the same. And in fact, they are. They're exactly the same. And they're all valid indexes into the array A because the numbers go from 0, which is the first legitimate number as an index into an array, all the way up to bar a bar minus 1, which is the legitimate index of the last element of array A. So are we still doing okay so far with the notation? Yes?
Why is the coda also that?
But we'll see later.
Oh,
Okay, we'll see why the codomain is also exactly the same as the domain. So what we'll do is now we introduce K. This is the initial condition. So when you give somebody an array and say, hey, Nick, go ahead and sort this array, you start to specify the initial condition like this. So let's start to read this a little bit. We have to add this criterion to the program. So K of something, K of I, is the initial value of A bracket I. That's basically how the K's are defined. And I hope I described it somewhere here. Did I describe K?
I think if you scroll up a little bit, you did at the top.
Yeah, I thought so too. Because that's the initial condition. Yep, there we go. So this is the initial condition. So the initial condition is like this, just so that we know what is the initial value of A bracket I. It is just K of I. Is that okay? So K of I is the initial value of array element A bracket I. Okay? That's how we define the K's. Okay? So knowing that, then we want to enforce this particular condition here. So what is this condition saying? It says, for any valid index into the array, that's what I is, we want A bracket I to be the same as the initial value of some A bracket I when we first started the program. Is that okay? Okay, let me say that one more time. We want, when the algorithm is done, this condition applies when the algorithm is done, has completed. So when the algorithm is done, I want each element of the array to contain the value of some initial value of the array when I started the program. Is that okay? Now, this condition alone is not going to be very helpful, right? Because I can just take the first element of the entire array, copy that value throughout the entire program, and would that work? Well, it would work because I can use the function to map everything to the first element. So it would actually work. But is that algorithm sorting? No. Okay. So we look at this and go like, it's not working either. It's not describing what sorting really means. Okay. So what do we need to do? We also need to have, we need to specify something about this function f. We need to say that, okay, guys, we cannot map everything to 0. We cannot map everything to 1. We need this function to be bijective. Okay, bijective, new word, haven't defined it yet. What that really means is everything in the domain has to map to something unique in the codomain. Okay, so let me say that one more time. We are now adding a new requirement of this function f. And we say each element of the domain has to map to one and only one thing in the codomain. That part is still there, okay, because that's the minimum requirement to be a function. But we are also adding the fact that we want whatever you map the domain element to is unique. In other words, no two elements of the domain can map to the same thing in the codomain. Okay, so we're adding that requirement now. And then we're combining that requirement with the original sorting or the ordering thing. So we are adding this part to this part using a conjunction. And then on top of that, we also have to specify that the function f has to be 1 to 1. In other words, the mapping has to be unique. So with all three requirements, 1, 2, and 3, now we can properly describe the result, the proper result of a sorting function, algorithm. Is that okay? All right. Now, we already talked about why we have to go through all this trouble to use mathematical notations to describe the proper output or the properties of the output of a program, because we want eventually to be able to have a program to evaluate an algorithm and to see whether the algorithm is correct or not. So that's how we connect back to the long, big, huge digression on Monday. Are we doing okay so far? Are we connecting kind of all the pieces? I mean, there's one piece here, which is one-to-one. What exactly does it mean? We'll talk about that later. So are we still doing okay so far? Are there any questions about any of these concepts? Because it's better to get all those concepts cleared up before we move on to talk about the properties of a function. Is it injective, is it surjective, or is it bijective?
Can you explain the first part again, like with the k, like when you're defining
Yeah.
k?
Okay, so the k's are used to specify the initial condition of the sorting algorithm. Okay, so I'm just saying that okay, this is what we know about the array before you sort it. Is that okay? So we are basically just saying, okay, element 0, a bracket 0, has a value of k0. A bracket 1 has an initial value of k1. A bracket 2 has an initial value of k2, and so on. So this way we kind of keep track of the initial values of all the elements in the array.
K's like the constant, right?
The k's are constants, right? Yep. Basically, we're using it to keep track of, okay, these things were in the initial array before sorting. We better be finding all of these things again in the sorted array, just in a different order. That's basically what this entire discussion is about, is how do we describe that? Good?
Yeah.
All right. Excellent. Any other questions? That's a good question. Very good. Yep.
Why are they in two separate statements instead of the same statement?
Why are they in two separate statements?
The definition of sorting and also what you know.
Okay, so this is what we initially start with, because that's what most people would think of, but by itself is not enough to describe the result of sorting. So what we are missing is this piece here. So this piece is necessary, but this piece is also necessary, so that we don't just reinitialize the entire array to 0. But this piece by itself is also insufficient, because we can have a function f that maps all the indexes to 0. In other words, I just copy a bracket 0 throughout the entire array, and that will meet that requirement. So what is preventing me from doing that and calling this, this is my sorting algorithm? Professor Subsidiary, you have to give me all the points because I meet all the requirements, right? So the only thing that stops me from doing that simple algorithm that is not sorting is to add this part here. The function has to be one-to-one. Every element in the domain has to map to a unique element in the codomain. Once I add that one extra requirement, that completes the actual description of what sorting means. Is that kind of answering your question? Okay. So you can see I probably was a very bad college student, because I can find and see all the loopholes in everything. I'm only semi-kidding. Because I do see loopholes. I see a lot of loopholes in things. Cool. So are we good with this? All right, so we're going to move on. Okay. So when we move on, we are moving on to the next slide. You can see that I'm really just sequentially going through all the modules. This one is kind of long, so even though it is a module, it is going to take a little bit of time to go over this entirely. Okay, so it will start off a little bit simple, but by the time we get to the examples, it does get a little bit, I would just say it gets a little bit involved. Okay, so we start with the word injection. Okay, what does injection means? Okay, so injection is a noun, which is really saying the same thing as an injective function. So injection is a function with the extra property of being injective. Okay, So in this class, you can use the phrase injective function, or can use the noun injection. Either way is okay. You can use them interchangeably. So to use English, what injection means is each element of the domain is mapped to a unique element in the codomain. That's basically it. Okay, unique. All right. So what we'll do is we are going to say, okay, let's say f is a function. X is the domain and y is the codomain. So we already know that f in fact is a function mapping domain X to codomain Y. Okay? So the question now is, how do we specify this extra thing that makes it an injection? Okay? So one way to specify that is this statement here. Any function that meets this requirement, that makes this true, is an injection. So let's check out what this whole thing is saying. So we'll go step by step. For all p in X, in other words, bind variable p to an element of the domain. Okay? This is all nested. Okay? So while p is an element of X, bind element q, which is also in X. So now we have two variables bound to elements of X. Now, can I pick the same thing for both p and q? Yes, you can. Okay? So all this is saying, all p and q are saying is p has to be in the domain, q has to be in the domain. They can be the same thing. They do not have to be the same thing. Just pick something in X and put it into p and q. Is that okay? But in either case, you better make sure that this implication is true. So the first part, or the left-hand side of the implication, says if p and q are the same, don't worry, it's already done. Okay? We're not concerned. Is that okay? Because if p and q are really the same thing, then p does not equal to q is false. If the left-hand side of an implication is false, the implication is automatically true. So that basically just means if you accidentally pick the same thing for p and q, it's okay, don't worry. But what if you pick two different things from the domain? Well, then we better make sure that f of p does not equal to f of q. That is what the uniqueness comes from. Is if you have two different things, if you pick two different things from the domain, they better be different things in the codomain. Is that okay? So this is the mathematical symbol, or one way to use mathematical symbol to describe a function that is injective. Are we doing okay so far with what injection means? Go ahead.
Can you repeat the innermost nested part?
Yes. So the innermost part of the expression, where p and q are already bound to something in X, right? So this part basically says, if p and q turn out to be the same thing, if by chance you pick the same thing for variable p and variable q, don't worry, the implication is automatically true. On the other hand, if p and q are different, you pick different things from the domain, then they better map to different things in the codomain. Because when you apply function f to p and when you apply function f to q, they better map to different things. Is that okay? All right, cool. So the other way, by counting, you can also do it this way. You can also describe a injective function f using this particular constraint. So what is it saying? Okay. Now you have seen something like this before, but I tell you it's not exactly the same. Because last time when we saw something like this, it was for all p in X. This one is for all q in Y. Okay, so it's a little bit different. So what this is saying is for everything in the codomain, okay, pick something out of the codomain, q. Okay, so you hold on to q, okay, and you ask, is this going to be true? We want this to be true if function f is injective. So you hold on to q, q already has a value, and then what you need to do is to find a tuple in f where the second item of the two tuple is q. Okay, find all the two tuples where the second item is Q, put them together in a set, and then count. That count has to be, the cardinality of that set has to be less than or equal to 0. Less than or equal to 1. So it can either be a 0 or 1. Now, why can't it be a 0? It can be a 0 because you can have elements in the codomain that are not mapped to. It's perfectly okay. Injection doesn't say that you have to use up everything in the codomain. It simply says you cannot have two things in the domain mapped to the same thing in the codomain. Okay? It can also be 1 because, you can have it can also be 1 because if you do have something mapped to that element Q in the codomain, you better to make sure there's only one thing in the domain that maps to it. Yep.
What is the line in the center? I know the two.
You mean this one? Such that. Yep. That's cardinality. This is a pair. That's cardinality of.
So would you mind just reading the whole thing in English? I don't mind.
I think we can use a text-to-speech program to do this. I think next time I'll actually play around with that and see what happens. Okay, so it says for all Q in Y, the following has to be true. The cardinality of a set where each element of that set is a two-tuple from F, and then the second item is bound is the same as what we have chosen as Q. That set has to have a cardinality that is less than or equal to 1. It's really hard to say it because, in normal, in most natural language, they don't have the concept of nesting. So nesting is kind of a construct that you have in your mind, but it is not explicitly specified in the language. So that makes it kind of really hard to say things that are very structured and where the nesting really makes a lot of difference. Yep.
I think what makes this difficult is that we're naturally reading it from left to right.
Mm-hmm.
We're not reading it from the center outwards.
Exactly. Well,
In some cases.
right. So, so related to your comment, okay, this is all because, we got poisoned by a notation called infix notation. So do you guys want me to go into that digression? The whole thing about, why infix is bad? No, not yet. Okay, fine. I'll take no as not yet. Because at some point in this class, I think we might encounter that concept, infix versus prefix versus postfix. Okay, so let's go through some examples, okay, and we'll see whether those functions are injective or not, okay? So I'm going to use my notepad for that purpose, okay? And I'll leave this definition up here, and we'll say f is a function that maps ABC as my domain to the codomain of 0, 1, 2. Okay. Well, let's make this a little bit more. 0, 1, 2, 3. Okay. So now I actually define f as a set of two tuples. Now remember, f has to be a function first before we even ask, is it injective? So I cannot give you a non-function and ask you whether it's injective or not, because the word injective means it is a function already. Okay. So I'm going to say A maps to 0, B maps to 1, and then C maps to 2. Is this injective or not?
Yes.
It is injective. Okay. Then you ask, but Tech, what about the case when we choose 3, which is in the codomain, as our Q? What happens in that case? The cardinality is 0, which is allowed, because it just has to be less than or equal to 1, which means at the most 1. Okay? So this is injective. Okay. Let's take a look at the second one. Okay? We have A, 0, B, 0, and then C1. Okay. Is that injective or not? It is not injective. Now, using the first one, you can kind of see it, right? Because if P is A and then Q is B, then A does not equal to B, okay? But f of A and f of B are the same because they both map to 0. So you can see how the first definition of injective or injection also works. But we want to look at it from the perspective or the lens, through the lens of the second definition. Okay? Why does it fail this test? Which element do you want to choose as Q in order to fail the test? 0. Okay, very good. Okay, so when Q is 0, what is in this particular set? A0, B0, there are two tuples that meet that requirement. So this particular set here now has 2 elements. So the cardinality of that set is going to be 2. 2 is less than or equal to 1 is false. And therefore, it fails this test. So are we doing okay so far with both of these examples? Okay. Very good. So I'm going to write down here and say this is not injective. Yep. Everything in the domain has to map to one and only one thing in the codomain if it is already a function. And both of these examples meet that one requirement. Okay, so that's basically injection. So we'll move on to surjection. Okay, so surjection basically just means that everything in the codomain need to be mapped to. Okay, that's it. Everything in the codomain has to be mapped to. So one way to look at it is to say something like this. For everything in the codomain, there exists at least one thing in the domain so that that thing from the domain maps to the one thing in the codomain. Okay, that's one way to look at it. So we do okay so far with this definition. We go through everything in the codomain. Okay, we look at every single thing and we say, okay, let's look at this one thing in the codomain Q. And then what we are asking is there at least one thing in the domain P that maps to it? If the answer is yes, then we pass the test for that one element in the codomain. Then we move on to the next one, and the next one, and we want this condition to be true for everything in the codomain. So we do okay so far with this way of defining surjection, which basically just means everything in the codomain are mapped to. Can we map 2 things from the domain to the same thing in the codomain? Yeah, this doesn't say that they have to be unique. They just have to be all used up. Is that okay? All right. So alternatively, if you want to count elements in a set, this is how we can define it. For everything in the codomain, okay, pick some Q in the codomain, and then find all the function, group them into one single set. The cardinality of that set has to be at least 1. Yep.
Top one, f of p is q. Is
Uh-huh.
that the same thing as saying
PQ is in F.
pq is in f?
Yeah, they mean exactly the same thing in this class. Very good, good observation. So to just to mention to the whole class, f of p equals to q is saying exactly the same thing as open paren p comma q close paren is an element of f. Because in this class, we look at a function as a set of 2 tuples. Are we good so far with this definition? Okay. So you can see that in both cases, I'm going to scroll up just, okay, maybe I need to zoom out a little bit. Right there. Okay, so now we get to see how we define injection and how we define surjection. So let me just scroll a little bit because I need to show both comparisons. Okay, so when you look at the top, that's the requirement to be an injection. When you look at the definition at the bottom, the requirement to be a surjection. Do you see how similar they are? We are counting something, and what we are counting is exactly the same kind of thing. If you look at this expression here, and you look at this expression here, they are identical. What are we comparing to? is also identical. Is it less than or equal to 1? Or is it greater than or equal to 1? Doesn't this just beg you for the question of what if they are both true? Bijection. So if this count is exactly 1, then we have bijection. Bijection means it is both injection and surjection. When you have both of them true at the same time, then you have bijection. Are we okay with that concept? Good, okay. So if I scroll down just a little bit to talk about bijection, that's exactly how one way to define it is both injection and surjection. The same function is both. Are we okay at this point? Cool. All right. Okay, so let's go through some examples. Okay, so let's go through some examples that we have already gone through. And we look at this example here using the domain that is already mentioned here. This is our domain, and this is our codomain. So now the question is, we know this is a function. We also know this function is injective, but is it surjective? It is not surjective because 3 is not mapped to. Or the cardinality of the set, this thing here, is a 0. It is not greater than or equal to 1. Okay, so that is why. Okay, so it's good to use examples to kind of illustrate what we mean by injection, surjection, and bijection. Yep.
So, given this domain and codomain, we can't construct a bijective function, right?
You're absolutely right. Okay, so given the constraint that we already have of having 3 elements in the domain and having the codomain having more elements, it can never be surjective. Does that make sense? If the cardinality of the domain is less than the cardinality of the codomain, that function can never be surjective. Now, can it be injective? Yes, it can be injective, but can it be surjective? The answer is no, it cannot be surjective. Now, what if the cardinality of the domain is greater than the cardinality of the codomain? Then it can be surjective, but it can never be injective. Because it has to duplicate at some point. You don't have enough things in the codomain to maintain the uniqueness of the mapping. Yep.
Requirement of a function that the domain has to be mapped, like every element has to be mapped.
For injection or
For it to be a function.
for a function?
Yeah.
So for a function, they can all map to the same thing.
Right,
Because
but
the
everything in the domain has to be mapped to something.
yes, it has to map to one and only one thing in the codomain. But whether it's unique or not is not specified when you just want a function. But if you want an injective function, then it has to be unique. All right. Are there any questions at this point about injection, surjection, and bijection? Bijection is just both, basically. So if we have a bijective function, if I tell you f is mapping x to y and it is bijective, you automatically know the cardinality of f, x, and y, they're all the same. They all have to be exactly the same. Is that okay? Are there any questions about that statement? Okay, let me write it down. Okay, so this way we can look at it. Okay, if f is a function, it maps x to y, is bijection, is a bijection. Okay, there we go. Then one thing we know for sure about the cardinality is f has the same element as x, which has the same number of elements as y. They all have to be the same. Now, the first part has to be true if it is a function. Okay, the cardinality of f and the cardinality of its domain, they have to be the same anyway. Because remember, the number of mapping has to be the same as the number of elements in the domain. because everything in the domain has to map to one and only one thing in the codomain. So the cardinality equality between f and x is kind of a given. Okay, if it is a function, those two have to be the same. But if it's a bijection, if I tell you f is a bijection, then you also know that the cardinality of y also has to match the cardinality of the other two sets involved. Is that okay? All right. So why do we care so much about bijection? Because the term injection and surjection, those two terms, is really just an easier way to get to bijection. Okay, it is bijection that we really want. So why do we care about bijection all that much? Because if you have a bijection, then the function has an inverse. It is reversible. Whatever you do to go from x to y, it is reversible. If you tell me where you map to, like in y, I can tell you what you used to map to that value. It is reversible. Okay? So reversibility is a great thing. It's really a great property of a function. So we'll talk a little bit about the notation here. Okay, so if I tell you that f is a function, it maps domain x to codomain y, and it is bijection, is a bijective function, then we also know that there exists a function that we call f inversed, where it maps y to x. So the original function's domain becomes the inverse's codomain and vice versa. Okay, such that for every element in x, the inverse of f applied to the f of e is really just e. I think most of you know what the inverse function is. Okay, it's kind of like sine versus arcsine, tangent versus arctangent, log versus versus exponent. Okay, so they can basically undo each other. Okay. And we know this already, okay, because the cardinality has to be 1. And in this case, it doesn't really matter whether we say for every p in x or for every q in y, because it's reversible. So you can pick something from the domain and mention the cardinality, or you can pick something from the codomain. It's going to work out equally anyway. So are we okay so far? So that's why this actually is the same thing as that when we describe a bijection. Actually, I take it back. I take it back. This is what makes a function function. This is what makes it a bijection. So I take it back. I was wrong about that. All right. So we kind of okay with all this description? All right. So given f is a bijective function, this is one way to define f inversed. Okay, so let's check out what this is saying. For every p in x and then for every q in y, if pq is an element of f, in other words, if f is mapping p to q, this thing is true if and only if qp is also in the inverse of f. I mean, that's just really just kind of, it's somewhat obvious, but that's one way to describe an inverse function. It is also basically saying f of p is q if and only if f inverse of q is p. So that's the other way to say it. Are we still doing okay so far with all this stuff?
So you're saying the second one and the fourth one are the same?
The second one and the fourth one. You mean this one and this one?
Yeah.
Yes. No, they are not the same. Sorry, I take it back. They're not the same because the second one defines what things should be in f and f inversed, and then this one is really just saying how do we know something is bijective. All right. So are we doing okay so far? Okay, so I'm skipping some of these reasonings here, and means so just expressions. And I'm skipping all the way to the bottom. If you look at f inverse as a function, does it surprise you that the inverse function of f is also a bijection? It should not surprise you at all that if f is a bijection, then f inverse is also a bijection. All right. So we are okay with injection, surjection, and bijection. Are we good? Now, do you guys remember I said one time the cardinality of a set that has an infinite number of elements can be compared to the cardinality of another set that also has an infinite number of elements? Do you guys vaguely remember that discussion? Like I can say, the number of elements in the set of odd numbers is really the same thing as the number of elements in the set of all the even numbers. Remember that? Okay. So the reason why we introduce bijection is to facilitate the comparison of cardinality of sets that have an infinite number of elements. And we can say, is this really having the same number of elements as that? Wait, hold on a second here. This thing has an infinite number of elements. That thing also has an infinite number of elements. How do we compare this? Right? The idea is if a bijective function exists between these two sets, then we say they have the same cardinality. Okay? So we will get to that right next to this. Okay. So I'm not really sure whether you guys have any questions or not, because we kind of go through these concepts really fast. So I'm not going to give you the function assignment at this point. I might give it to you on Monday, because I want you guys to have some time to have these concepts to sink in, okay, before I give you the homework assignment. Is that okay? Or do you guys want to have it now? Okay, give you guys a weekend so they can kind of have the concept sink in, okay? So the next topic is called Aleph-Null, okay? So this is the next topic. We'll get into it because this connects to bijection. Yep. Go ahead.
Even if you don't have the actual assignment, can you have an upgraded assignment just on the...
Yeah, I plan to give you guys something to work on over the weekend so that it can help to consolidate your understanding of injection, bijection, and surjection. Okay, very good. If you don't get it by tonight, you'll just send me an email to remind me. Yep. All right. So Aleph-Null. So the first thing is we want to consider the set of all natural numbers. Okay. Do we know what natural numbers are? Can someone tell me what natural numbers are? They're not just integers. So there's a slight disagreement within the mathematics society. Some people say natural numbers should include 0, and some people say natural numbers should not include 0. So some people say, well, but if you include 0, it is natural number. If you do not include 0, it's called counting numbers. Okay, so there's a slight discussion of whether 0 should be included or not. I don't really care. Okay, because whether 0 is there or not, we just shift the whole thing a little bit, okay, and that's it. But for the rest of the discussion, we'll just say that yes, 0 is a part of natural number. Okay, just because I have to choose one definition, I'm going to choose the one where 0, 1, 2, 3, 4, those are the natural numbers. Okay, so you can look at those as the non-negative integers. Question? Nope. Okay. All right. How many elements do we have in the set of natural numbers? Infinite number, right? Because if you say, oh, this is going to be the last natural number, it's called n, and then I'll ask you, what is n plus 1? And you go like, dope, right? So we use this notation, the funny-looking n, to represent the set of all natural numbers. And then the cardinality of natural number is, by definition, Aleph-Null. Okay, so this kind of squiggly version of n is Aleph. It's Aleph-Null. And that is by definition. This is just how we define the symbol of Aleph-Null. Okay, so now we want to look at the equivalency of cardinality. So now that we have defined what is Aleph-Null, then we want to look at the set of all integers, and then we ask, can we compare how does the cardinality of the set of all integers, including the negative ones, compare to the cardinality of the set of all natural numbers, which are the non-negative integers? How do they compare? Is one greater than the other one? Do they equal? I mean, how do we relate those two? Okay, so that's the question. So what we want to do is we ask the question, can we find a bijective function? Can we find a bijective function to map the domain, which is the set of all the integers in this case, to the codomain, which in this case is the set of all natural numbers? If I can find such a function that is bijective, mapping from the set of all integers, including the negative ones, to the set of all the natural numbers, then we can say the cardinalities are the same. Does it make sense to you kind of intuitively? Okay, because if I can map everything in here to something unique over there, it means I can also map something here back to something over there, and it's unique one-to-one. So it kind of makes sense that they have the same number of elements that we can actually compare and say they are equivalent. Is that okay? Okay, all right. So how do we make such a function? I mean, it's right here on the screen, and I think I'm gonna guess half the class look at that and go like, oh, okay, I can see how it's defined, and the other class will look at what is the question mark and the colon doing in an expression. So that really kind of, that way I can tell who have at least taken one class from me. Because I use the ternary operator a lot in all of my classes. Doesn't matter what I'm teaching. Okay, so this is called a ternary operator because not every single one here has taken at least one class from me, so I'll explain what a ternary operator is. A ternary operator means there are three parts to the expression. The first part of the expression, which is whatever is to the left-hand side of the question mark, is a condition. Evaluate the condition. It will either be true or false. Okay, that's the first part. If the condition is true, then the middle part, which is the part that is between the question mark and the colon, is the value of the entire expression. It is called the true value, or the value when true, okay, for the entire expression. And then the last part, which is the part that is to the right-hand side of the colon, is the value of the entire expression if and only if the condition is false. So what you really have is if, then, else. But it's encoded in a way that it is a single expression without the need to use statements. So are we doing okay so far with understanding what a ternary operator is? Okay, this is, I did not invent the ternary operator, in case somebody is wondering. This is actually an operator in C. Okay, are we doing okay so far with the interpretation of the ternary operator? Okay, so once we know what the ternary operator is, I then claim that this f, function f, is going to map all integers to natural numbers, and it is a bijective function. Yes?
So ternary operator and tertiary operator mean the same thing.
Oh, I just call it ternary operator.
Okay.
Tertiary operator?
In the PDF itself, it says tertiary operator.
Oh, okay.
Are they interchangeable, or is it just ternary operator?
I could have used the wrong word, so let's double check. Okay. Yeah, it's ternary operator, but it might also be known as a tertiary operator. So ternary for sure is the correct one. So we can look up tertiary. So do we want to just kind of stick with ternary? Ternary is good? Okay. You're curious now. Okay, well, let's check it out. Where is... Hmm?
I know what tertiary means, but I don't know why it would be.
Yeah, why would we use, say, it's accessory to, right? Tertiary. Okay, I think it's just a typo. Yep, it's just a typo for me on my part. Okay, let's fix it. We'll fix it right away. And this is module 0293. And we're looking for tertiary. Whoops, there we go. There we go. That's the only occurrence. Okay, very good. And I have to change. I killed one of my servers, so I have to use the power server to host all my nodes now. So I have to change that script too. Oops. It says oh, okay. I just put in an extra backtick. There we go. All right. So this is how I write my class notes. It's a typesetting program called LaTeX, which looks like LETX, but it's not. It's LaTeX because it's LA. So the L and the A are actual letters from the alphabet, and then the so-called TEX is tau epsilon chi, which is Greek. So it's actually not LaTeX. It is LaTeX. All right, done, fixed. All right, so it's a ternary operator. So, but how does it work, right? So let's try some values, right? Because I claim that if x is an integer, it will be mapped to a natural number. So what number do you want to try? 0. Okay, so 0. So f of 0, 0 is greater than or equal to 0 is true. So we're going to use the then value, which is 2 times 0, which is 0. So 0 maps to 0. No problem. What else do you want to try? Negative 1. Okay. So f of negative 1, x is negative 1. Negative 1 is greater than or equal to 0 is false. So we use the else value as the overall value of the ternary expression. So negative 2 times negative 1 is 2. 2 minus 1 is 1. So that means negative 1 maps to just 1. Okay? What else? I mean, you need more numbers to see a pattern. So let's try 1. Okay? 1, x is 1. 1 is greater than or equal to 1. We just return 2 times 1, which is 2. So 0 maps to 0, 1 maps to 2, 2 maps to 4, 3 maps to 6, and so on. So if you give it something that is non-negative, it maps to the even number corresponding to that. Okay? If you give it something negative, let's say negative 2. We tried negative 1 already. Let's try negative 2. X is negative 2. Negative 2 is greater than or equal to 0 is false. Go to the else value. Minus 2 times negative 2 is 4. 4 minus 1 is 3. So what it does is it maps all the negative value to odd numbers and all the non-negative numbers to even numbers. Okay? So it's definitely a function. Okay? The question is it bijective? If I give you a natural number, do I know which integer maps to that natural number? Well, the first thing you do is you figure out, is it even or odd, right? If it's even, you divide it by 2, you're done. If it is odd, then you have to reverse this operation, which means you have to undo the last thing first. So you have to add 1 and then divide it by -2. That will get you back to the original negative integer that mapped to that odd number. Okay? So it's a bijective function. So that kind of makes sense, right? The set of all integers versus the set of all natural numbers. You kind of go like, yeah, I can see how this maps out. So before we go, okay, I want you to think about it, but also try to read the notes ahead a little bit. If I give you a grid system, okay, which is kind of like the pixel system that we have on any raster devices, okay. So I call this, the lower corner here 0, 0. Then we have 1, 0, 2, 0, 3, 0. And then this is 0, 0. This is 0, 1, 0, 2, 0, 3. And this cell over here diagonally is going to be 1, 1, and so on. So you guys know the two-dimensional coordinate system already. Yes? So what if I were to tell you that the cardinality of the set of all 2 tuples, where each item of the 2 tuple is a natural number, if you consider that particular set, it really has the same cardinality as the set of all natural numbers. Does that make sense to you? A two-dimensional thing really has the same cardinality as a single line in terms of integers or natural numbers. It makes sense to you? And if it makes sense to you, then what is the function? Okay, what is the function? What is the function to map a two-dimensional coordinate to a single natural number? Once you figure out the function, then what is the inverse function? If I give you a natural number, I will ask you which coordinate is mapping to this particular natural number. So all of those questions are answered in the rest of this module. And I'll give you a quick scroll through. You can see where this bar is, and it just keeps going and going and going and going and so on. A lot of quadratic equations, yes. And I'll explain all of that next Monday, but it will definitely help if you try to read ahead of me because there's a lot of concepts involved.
So regarding a 2-2